spectral analysis of rotation map. If you remember, we have established with you that the rotation map, it's the one which has the following metrics. If you rotate by the angle, I use the letter theta for the angle. If you rotate by the angle theta, that's how the metrics of this linear map will be. It's a linear map, and that's the metrics of that linear map. I'd like to do the spectral analysis of this particular metrics. Yeah, I'd like to do a spectral analysis of this particular matrix. So if I compute my characteristic polynomial, which we know it's a determinant of this matrix, A take lambda I2, if you remember 2 days ago, for 2 times 2 matrices, we discussed with you shortcuts which help you solve or find characteristic polynomial in a quicker way. Here's a shortcut. I don't have to compute the determinant. All I have to do is this. I have to tell you that the characteristic polynomial will be quadratic polynomial with the second coefficient equal to the trace of the matrix, and the last coefficient equal to the determinant of the matrix. If you remember, the trace was the sum of the entries on the diagonal, and determinant, we know how to compute that. It's a product of the main diagonal, take the product of the opposite diagonal. In case of this matrix, trace obviously is a double cos, should be A capital here. Trace is obviously double cos. Determinant, if you take the product across this diagonal, it's a cos square. If you take the product across this diagonal, it will be negative sine square, so it is plus sine square. And due to the fundamental trigonometric identity, this is simply 1. So my characteristic polynomials becomes like this. As we discussed with you 2 days ago, it is very often just by knowing the trace and the determinant, you can guess the eigenvalues. It's not the case in the current presentation, because just having 2 eigenvalues which sum to double cos and which products to 1, can you guess those 2 eigenvalues? Can you guess 2 numbers which sum to double cos and which multiplies to 1? That's right, the 2 values are plus minus e plus minus I theta. I mean, if you're unable to guess that, you should follow the formulae for the solutions of the quadratic equations. Here's my formulae. If I try to solve this equation, that will be simply, that will go like this. The 2 roots are cos theta plus minus root cos theta squared, take 1 divided by 1. This one, again, by the fundamental trigonometric identity, it's negative cos square theta. Negative makes it I, and you end up with this expression, which is a Euler formula. So if you are unable to guess that, then you can do the complete analysis of your quadratic equation. You will find these 2 roots. At this stage, what should I say? At this stage, I should say that, surprise, surprise, my matrix doesn't have any eigenvalues. Because yes, we found the roots to the characteristic polynomial, but roots are not within the scalar field we consider my matrix in. So rotation matrix, as a matter of fact, in 2 dimensions, it doesn't have eigenvalues, which is expectable actually, because remember what the geometrically eigenvalues and eigenvectors, it's such a vector which is just simply scaled by your matrix. Obviously, rotation doesn't scale any vector. From a geometrical point of view, if you rotate vectors on the plane, none of the vectors get scaled. However, if you change the setting, if you consider your matrix within the other scalar field, if you do that, this matrix now loses its geometrical background because it's no longer the rotation. It was a rotation when you lived in this vector space, In this vector space, this was a rotation. It was a regular plane. But this matrix, if you change the scalar fields, the matrix becomes acting on in this vector space. And this vector space, we have no geometrical understanding what the space looks like. It's no longer the plane. So my matrix acts in that space, but is it a plane? No. In the conventional sense, of course. That's why we're changing the setting in order to accommodate these complex eigenvalues, but at the expense of dropping the geometrical interpretation. Well, yet we can finish the analysis, of course. Now having two eigenvalues within this larger vector space, so as eigenvalues, that's right. We can now hunt after the eigenvectors. Given the such nice structural look of my eigenvalues, I can find both of the vectors at the same time. I mean, both vectors attached to both of the eigenvalues by using plus and minus method. So I need a vector in my larger vector space such that the vector is non-zero and such that my vector is in the null space of this matrix, A take lambda I2. I will write this matrix now, and I will write this matrix for both eigenvalues at the same time by using this plus and minus technique. So look at this. The matrix A take lambda I2 is this matrix. If you take this value, if you subtract from this diagonal, cos will be gone. What will stay is negative plus or minus plus I sine theta. And here you got negative sine theta from this entry. Now you got sine theta, and here will be minus plus I sine theta. So you see I'm combining two analyses in one line by using plus and minus or minus plus. So what I'm saying here is that for plus here, you have to choose minus here, and for minus here, you have to choose plus here. That's why it's in the opposite order. Sine theta, obviously, it's a common factor, which I will put in the front, and the remaining bits is this matrix, or these two matrices. And now I have to guess a non-zero vector, x, which will vanish such a matrix. You can, of course, do it via row echelon form analysis, but this time the vector can be guessed. And here's my guessing. Look at this. For the first value, for the plus value, so when you have minus here and you have minus here, the vector is this. 1 take negative I. If I write it here, so the first component is 1, and the second component is negative I. Just look at this matrix and make just imagine you have only minus here and only minus here. Then such a vector will vanish the first row and will vanish the second row, because it will be 1 plus I square, which is negative 1 at 0. That's why this is the eigenvector within this larger vector space associated with this eigenvalue. Now, second eigenvalue with the negative, that's the one with the plus here and with the plus here. Again, vector is easily guessable. You just have to take plus here instead, and that will work. If you have plus here and minus 1 here, it works with the first row and it works with the second row, because it will be 1 plus I square again. So it's a negative 1. And that's the finish of the spectral analysis of the rotation map. Even though, strictly speaking, the analysis only works in C2 space, which is not actually, it's not the area where my map is in fact a rotation map. But still the analysis is over. Any questions?